I think I saw Wednesday into Thursday.
Yeah, honestly. No need to get the be there. Yeah, why I kept the I don't just all messed up everything.
Hi, everybody. Sorry to get everybody all distracted with the possibilities of snow days dancing in our heads, but so last time we had been talking about, or we've been talking about finding volumes, right? And we've seen kind of three-ish different methods now, maybe four if you want to count like the cross sections of similar shapes. One of which might be the disc or the washer, the donut shape. And we've talked about this other method of finding cylindrical shells, and we were kind of in the midst of this last time that we didn't kind of finish. I'd like to do one more kind of nice, slow, steady example of doing this. And then we'll take a break and let you guys do some practice just doing this kind of work. So let's look at this final example. It says find the volume of the solid obtained by rotating the region bounded by x minus x squared, y equals 0, and then about the line x equals 2. So like we're talking about, that's the region. And the line x equals 2, so that's what we're rotating about. So this is a classic shell problem, because if I try to, looks like going to be something with a hole in the middle, but for me to do the inner and outer radius, they're both on the same curve, right? So like the inner radius would go to here, and the outer radius would go over there. And how am I supposed to differentiate that if it's on two separate curves? That becomes kind of a problem. In these sorts of, it can be done, but these sorts of scenarios are like what cylindrical shells are kind of built for. Everybody's okay with that plan? So our formula is basically two pi r h, and I'm going to write this as r of x and h of x because these are typically, r and h are typically going to be functions, right? So because my axis of rotation is vertical, it tells me I'm going to be integrating along the horizontal, so this should be in respect to x. What I need to kind of sort out right away is a function to represent that r of x and a function to represent that h of x. So if I draw like a typical radius, it's going to come from the axis of rotation and then end somewhere into the solid, right? Each possible ending point in the solid is a radius that I'm going to be considering. The furthest one out is the outermost shell. The closest one to the radius is the innermost shell. But that's kind of what I'm going to be looking at here. So if I look at this point, this is like an x comma y, where I know this distance is the x part, right? Go ahead. It is in the testing. Part 1 is without, part 2 is with. So take it with you. Is that so far so good, everybody? And I know that this distance is 2. So that r of x has to be 2 minus x. Is everybody okay with that idea? So the height of my cylinder is going to represent just like that distance well, that's easy, right? That's just a function, which was x squared minus x. Oh, I'm sorry, yes, thank you. Does everybody feel okay as to how I came up with my functions for r of x and h of x? Now, the last thing I need to do is, since we're integrating with respect to x, is consider the bounds for my integral, right? So usually what I like to do is I think about my radius. The longest radius that I'd ever get would be from like there to there, right? The value for x then would be 0, right? And the shortest radius I'd get would be from like there to there. The value for x then would be 1. So that's going to be my setup. At that point, it just, you know, I would either you do your calculator or you FOIL that thing out and then integrate afterwards. I wouldn't, no need to do part or U sub or anything else. You just FOIL it out and grind that thing down. Does that feel okay with what we did there? On the setup. And that setup that we've, like I've drawn the two-dimensional version of, is really kind of the canonical setup, where the, you know, the radius is always going to be drawn from the axis of rotation back into that shaded region. And then the height of that shaded region is going to be like the height function. And it won't really matter if you rotate, you know, about a vertical axis or about a horizontal axis. It still kind of works the same way. Does that feel okay? I'm going to stop here and not grind through all the computation, because the setup is the part that's usually the stumbling block. If you get the setup, most people get to the answer afterwards. At this point, it's just getting through the setups. Yeah, Paulo.
To find the balance, you said FOIL out.
Oh, no. Not to find the bounds, to actually do the integral, right? Because I have the product of two functions here. I'd FOIL that out in order to actually compute the integral. The bounds we looked at by just looking at, like, what's the biggest radius that I'm going to have? And then what's the value for x for that radius? Well, the biggest radius it could have would be 2. So that means x equals 0. And the smallest radius it could have is 1, which means x would equal 1. So I integrate from 0 to 1. That's usually the easiest way to picture it. Sometimes the bounds are tricky to come up with if you don't think about it that way, but I usually just think about, like, okay, what's the biggest radius and the smallest radius I can have? And what value of x gives me that biggest and smallest radius for my radius function. Okay. So what I'd like for you guys to do today, with a partner, by yourself, either is fine, or with a small group even. It doesn't matter how many people are kind of working. But I'd like you to work on 37 through 45 from section 6.3, just to kind of show you what the direction is on these. So it says the region bounded by the curves is rotated about the specified axis. Find the volume of the resulting solid by any method. So that means that all mixed in here are going to be discs and washers and shells. So part of your first, or the first thing you should be doing after you sketch a little picture of what's going on, is figuring out which of the three methods is going to be the best one to use for this situation. Okay. Just to remind you guys, you know, if we're doing that, so let's just kind of take three different scenarios that are basically like the same thing. So let's say we have this, and I rotate that about the x-axis. What I'm going to have is like a football kind of shape, right? Is there any openings or indents or anything on that football? We call that a convex figure. If you have a convex figure, you're doing a disk. If I rotate it about a vertical axis, now there's going to be like a hole through the middle, or even if it's like a vertical axis like this, it's going to have like an indent in it. It's going to be concave, right? So it's either going to be a washer or a shell. The way that I would differentiate it is if the inner and outer radius is the same function, that's a shell problem. If it's not, it's a washer problem. Does that feel okay to you guys? So if this instead was like, I had an extra function like this going on in here, now that's a washer problem, right? If my region is this thing, that would then be, let me use a different color. Now that's a washer problem because the inner radius and the outer radius correspond to two different functions. I would do that as a washer. Does that make sense to you guys on kind of what we're seeing? That's my best advice to you, is to, like, when you're looking at the picture, how to kind of tell which of the three methods you want to use. I'm going to stop talking now. If you need a textbook, there's textbooks in that cabinet right next to Jennifer. You can use your digital one, whatever. I'll put the problems up on the board also, so if you want to just, well, at least, well, I can, yeah, I'll get them up on the board. And then just let you guys go to work here a little bit and try to make some progress and feel better about this process than maybe when we started walking, when we walked in. Okay, so if you want to get up and move around and sit by somebody you work well with, or if you just any and all of that is okay.
Okay, but you still had the same name, right? What are you talking about? Everyone's doing that. Oh, I'm sorry. Oh, just be careful. Yeah.